Begin. This is now the second lecture. So this is where we had sort of stopped last time. We were discussing how very accurate astrometric observations can help us to determine distances to various celestial objects. In the case of astronometry, to the stars in our galaxy. So why is distance determination important? Age of the universe? No, forget age of the universe and all. Just distance determination to a star, for example. Why is it important? Huh? Yes, to know its intrinsic luminosity. Remember, all the physics that you are going to do is not done with the flux. It is done with the luminosity, right? You'll have various models which will predict the luminosity of a star as a function of its mass or of time or any other variable. So in order to convert flux to a luminosity, you need distance. And that for the same reason, you need distance to some galaxy, distance to a quasar, distance to the cosmic microwave background, anything. You need distances in order to convert fluxes to luminosities, because fluxes you can measure easily, luminosities you cannot measure easily. So that is why astrometry is so important. And what Gaia has allowed us to do is to make out to about 10 kiloparsec, which means to the center of our galaxy and beyond. I've told you that the center of our galaxy is 8 kiloparsecs away from us. So up to the center of the galaxy and beyond, we are able to do lots of things. So we won't go into the details of this right now, but we will revisit this figure at a later stage when you better understand what is a rotation curve, what are globular clusters, what are Cepheid variables, what are RR Lyrae, okay, what is dark matter, what is the dynamics of the Milky Way, and so on. So, but I just wanted to flash this to you to tell you that within the last decade or so, just this one observatory has made many advances in many different directions and has greatly improved our understanding of our galaxy, and through that indirectly the understanding of other galaxies as well. Okay, so now we jump back, and I'm going to talk today mostly about the solar system. So all of you know this. So there are 4 inner planets. There's the asteroid belt. There are 4 outer planets. Pluto, which used to be a planet, got demoted in 2006. It's now what is called as a dwarf planet. And then beyond that, there are what are called Kuiper belt objects. And at the center of it, of course, is the sun, and it's our nearest star. And it is the only, other than the moon, it's the only astronomical object where you have to cut down the light that you receive when you study it. For every other astronomical object, you wish that it was brighter and bigger and so on, so that you could study it more easily. But the sun is so bright that it saturates all our detectors. Therefore, you have to have what are called neutral density filters, which means you cut down the light by a large amount so that you can image it or study it in other ways. Okay. So composed of the sun, planets, moons, asteroids, comets, and dust. So these are the main constituents. It formed approximately 4.5, maybe 5 billion years ago. Okay. So how do we know this? Is there some way of knowing? Huh? Yes. So radioactive, knowing the half-life decay time scales of various elements, you can try to determine what is so that is called radioactive dating. You can determine the age of rocks on the Earth. And the oldest rocks on the Earth are of comparable age. And from models of star formation and from observations of protostars, we know that the formation of the planetary system and the formation of the star usually happens concurrently. Okay, it happens at approximately the same time. So it is not as if a star forms and then a billion years later it forms planets. It's not like that. It seems to happen all concurrent. Therefore, we think the solar system is roughly this old. It's of course a gravitationally bound system, and it extends from the sun to the outer edges of what is called as a Oort cloud. We'll come to that Oort cloud, what the Oort cloud is, and can be sort of logically divided into the inner solar system and the outer solar system. So the sun is the central star of our solar system, and it is 99.86% of the mass of the solar system is the sun. So it really, really dominates everything, and whatever remains, Jupiter dominates that. So really, if you are looking at the solar system from a distance, you really only have to worry about the sun. So the movement of the sun, the kinematics of the sun, all these other things are like test particles. It is what is called as a main sequence star. We are going to come a little later when we talk about stars, that what are the main types of stars. But very roughly, if I were to say, one can say that there are massive stars and less massive stars. The more massive stars are more luminous and they have shorter lifetimes. Naturally, because they burn up, they convert their hydrogen to helium much faster, and they use up their nuclear fuel very quickly. And so the massive stars have short lifetimes. The less massive stars have much longer lifetimes, longer than the age of the universe for the least massive. So the G-type is, what is it? You think it's a sort of low mass star or a high mass star? Low, it's on the low side. So the sun has an approximate lifetime of 10 billion years. So it has completed about half its lifetime at the present time. After another 5 billion years or so, it will end. Does anyone know how it will end up? Red giant, and after that, it'll become a white dwarf. Correct. So it'll become a white dwarf eventually, but right now it's a stable main sequence G-type star. And it really is stable because its luminosity does not vary by more than 1% in each direction, even in the extremes on timescales of years. But it is on a daily basis, it doesn't change. It's what is called as a non-variable star. There are some other stars which we will study when we study variable stars, whose brightness changes, whose luminosity changes quite a bit over timescales of days or months. But this one doesn't. It's very stable, which is good for us because we know the Earth environment therefore becomes very stable. It's a massive fusion reactor, converts hydrogen to helium, and it burns 4 million tons of mass every second. Burns meaning converts, where you put E is equal to delta mc square. That delta m is 4 million tons. You plug in the numbers, you'll get the luminosity of the sun. Okay. So what are some solar properties? It is 1.4 million kilometers in diameter. It is 109 times the diameter of the Earth. Okay. So do you think it will be 1,000,000 times more massive? Is that reasonable to expect? If the density is the same, it will be 1,000,000 times more massive. It turns out that the density of the sun is less than that of the Earth. It's about 1/3 or 1/4 thereabouts. So it is not quite 1,000,000 times, or it's just about 1,000,000 times more massive than the Earth. Its surface temperature, which we call as the temperature of the visible surface, which is called as the photosphere, Photosphere has a temperature of about 5,800 Kelvin. But at its center, the temperature is much higher. Okay, it's about 15 million Kelvin. Okay. Even this is barely sufficient to fuse hydrogen into helium, but quantum tunneling effects come into play, and therefore there's a non-zero probability or a reasonable non-zero probability of hydrogen fusing to helium, and which is what is happening only in the core. There's no fusion happening on the outside. Remember that. It's only in the core. And it drives the solar system's dynamics and energy. So here's a plot or a picture of the anatomy of the sun. Okay. So what's on the inside, what's on the outside, and so on. Let's see if this works. So this is 1.4 million kilometers. And at the center, there is the core. And core is where the sun generates all its energies through nuclear fusion. Okay. But remember, the sun, is it a ball of gas? No, it's a ball of plasma. Okay. And therefore, what happens is, even if energy is generated here, it takes a long time for it to come to the surface, because within the plasma, if a photon is generated, it can travel only a short distance before it gets scattered, because it's a fairly dense plasma. It's not a low density plasma, it's a high density plasma. And so anyway, so slowly the energy keeps coming out. In the region immediately outside the core, colored in orange over here, it is known as the radiative zone. And it is in this zone that the energy that is created in the core slowly is diffusing through the plasma and coming out. In the outer region, outside of the radiative zone, is what is called as the convective zone. And here, the energy transport is not through radiation, but primarily through convection. So there are flows that are set up, circular flows, where energy is taken from the inside, deposited on the outer surface, and then the material falls back inwards and so on. Okay. And the relative size of the convective zone and the radiative zone depends on the mass and luminosity of the star. So when we come to stars, we will look at this idea again and see which stars are convective and which stars are more radiative. Outside of that is the layer known as the photosphere. And the photosphere we refer to as the visible surface of the sun. So it's like the surface at which below which you can't see, because the optical depth is too high for you to penetrate through that. And so it's what we call as the visible surface of the sun. And we can use Wien's law and measure the surface temperature. You can fit, it turns out that the sun is also a reasonably good black body with lots of absorption lines called Fraunhofer lines, but it's a reasonably good black body. So you can even fit the Planck function to it. And you will then get a temperature which will be that 5,800 Kelvin. Outside the photosphere is a layer called as the chromosphere. Okay? And here the density of plasma drops drastically. Okay, and that's the reason that chromosphere is optically thin, and you can actually see through the chromosphere and see up to the photosphere. So here the density of plasma begins to fall very, very dramatically. Before we go there, on the photosphere, you often see granulation. These are small, short-lived, grainy features that cover the sun, caused by thermal currents rising from below. So it's almost like a bubble kind of thing that is in the plasma, which is coming up and giving you these grainy structures. So if you have looked at any very close-up photographs of the sun, you will see that kind of, it is fragmented into little pieces. There are also on the photosphere darker, cooler areas, which are known as sunspots. Okay, and here the magnetic field is more concentrated. The sunspots look dark not because they're really dark. They're only relatively dark because they are cooler than the other parts of the photosphere. So sunspots. Then sometimes you see what are called prominences. This is this kind of looping structure, which is something that comes out of the sun, and due to the magnetic field, the plasma sort of bends downwards again and falls back onto the sun. This is many thousands of kilometers in extent, and the larger prominences are so large that you can put the entire Earth through the loop. They're so big. Then beyond the chromosphere, so before we go there, one more thing. There is something known as a flare, which is a rapid unidirectional ejection of energy. It mostly comes out in the form of radiation rather than particles streaming outwards. But more dangerous or more disruptive for Earth people is something known as the coronal mass ejection, which is vast eruption of billions of tons of plasma and accompanying magnetic fields from the sun's corona. Now, what is the corona? So, outside the photosphere, there is a region which is known as the transition region. It's a thin, irregular layer that separates the relatively cool chromosphere from the much hotter corona. Okay. Now, this much hotter corona is a real problem. It leads to one of the biggest problems in solar physics, which is the coronal heating problem. Okay, we'll come to that in the next slide. But right now, just remember that starting from the sun, where we said it's 15 million Kelvin, it has cooled down to about 5,800 Kelvin at the photosphere and about 4,000 Kelvin or 3,500 Kelvin in the chromosphere. After that, the temperature, instead of cooling further, actually begins to go up. Okay? And in the corona, it becomes once again like a million Kelvin. It becomes very, very hot. So the corona has very low density. So the density continues to fall of the plasma, but the temperature begins to rise. And why that rises is the big question. It's called the coronal heating problem. What is causing the corona to heat up to these high temperatures? Okay. Now, there are a couple of other things. So there is the solar wind. So the corona is the sun's outer atmosphere, which extends millions of kilometers into outer space. It's very hard to study because it is quite faint in the optical. However, because it's very low density material, it can be seen in X-rays because of the high temperatures, but it can be studied in the optical during solar eclipses, because there the main photospheric disk is completely covered, and then the corona becomes nicely visible. And there have been many studies of the solar corona during total solar eclipses. But in addition to this, there is something known as the solar wind. Okay? A continuous stream of charged particles which are coming out of the corona. Okay? Because this is just plasma, right? It's like boiling plasma, and it's continuously ejecting material. So not only are photons streaming out of the sun, a stream of particles are also streaming out. Protons and electrons. What is the size of the core? The size of the core is about 1/5 the diameter of the sun. And again, the relative size of the core, radiative zone, and convective zone is a function of stellar masses and luminosity. We'll come to that when we talk about stars. Yeah. So coronal mass ejections are the real danger thing. So there are people who study space weather. They are constantly worried about these coronal mass ejections coming and hitting the Earth. Okay, because when they hit the Earth, then it can cause damage to all kinds of communication satellites. It can because we have a nice magnetic shield. It doesn't affect us directly, but all our satellites can be damaged. Sometimes there have been instances where satellites have been destroyed by a coronal mass ejection. Okay, so the coronal heating problem. So something is happening which is continuously heating the outer corona of the sun. So there are various kinds. There are basically three classes of models. Okay, so there is something known as wave heating. Okay, so magnetohydrodynamic waves, for special kind, they're called Alfvén waves. They propagate from the lower layers of the sun's atmosphere, and these waves continuously carry energy, and they are dissipating that energy into the corona, and they're continuously heating it. The second possibility is the role of the magnetic field through the role of magnetic reconnection. Sun's magnetic fields lines can become tangled with each other and then snap back into place. So when the field lines break, this releases significant amounts of energy. And it is believed that there are what are called nano flares, very, very low energy flares, which are very low in energy, but they're extremely frequent. They're happening continuously. And these are all magnetic reconnection events. And these may contribute significantly to the heating of the corona through magnetic reconnection. There is also Alfvén wave turbulence. So these Alfvén waves, as they propagate through the plasma, they can become turbulent. And this leads to what is called as a turbulent cascade, wherein the waves sort of break up to smaller scales. So the waves sort of fragment into smaller length scales. And once that happens, then it becomes easier to dissipate the energy that they contain in the form of heat energy. But now, which of these mechanisms operates in the sun and in other stars? And what is the relative importance of these? And is still an active area of research. And there are a number of probes. So there is something known as the Parker Solar Probe, named after Eugene Parker, one of the pioneering solar astrophysicists. Aditya L1, our own ISRO's satellite, and the ESA solar orbiter. So all of these observatories are continuously studying the sun. And one of the main problems that they're trying to answer is the coronal heating problem. So it's a difficult thing. It's very complicated. People try to do it with observations. People try to do it with simulations and so on. So at NCRA, for example, nano flares are something that can be studied in the radio. So using the Murchison Whitefield array, Divya Oberoi and his students, they are looking at the contribution of nano flares to the heating of the solar corona. So many people are attacking the problem in different directions. So this is Aditya L1. So Aditya L1 has a number of instruments on board. And this is very characteristic of all large space observatories, because you spend so much money on building and sending the space observatory, it doesn't make sense for it to have one instrument. You put 5, 6, 7, whatever you can fit in, you fit in. The main instrument is this one, the visible emission line coronagraph. And the main purpose is to study the solar corona and the origin of CMEs. The CMEs, if there need two or three things you need to know about them. One is how energetic they are. Will they cause problems to Earth? B, are they going to hit the Earth? Because if the CME is going off in some other direction, doesn't matter. You don't have to worry about how energetic it is and how much pre-warning can you get. Because these things move very fast, but obviously they don't move nothing close to the speed of light. What is the light travel time between sun and the Earth? It's about 8 minutes. Okay, so obviously it's going to give you much longer notice than 8 minutes. It can be many hours or sometimes few days and so on. That is important. There is also an ultraviolet imaging telescope, and this can be used for imaging directly the photosphere and the chromosphere. And this can be used to study the properties of the solar wind. And solar wind, mostly ions. You can do an ion analysis, which are the various species, ion species that are present in the solar wind. And there is an X-ray spectrometer, which can study solar flares. And this is another higher energy X-ray spectrometer, again studying solar flares, but now at the higher energy X-rays. And this is a magnetometer for measuring the strength of the interplanetary magnetic field. Where do you think this satellite is located? L1. Okay. And there is an interesting story behind this. I don't know how true it is, but the story goes as follows, that originally this mission was called the Aditya mission. Then somebody in ISRO said that, okay, we have not sent any satellite to L3 and L4. So why don't we send Aditya over there? Okay. And suddenly these guys panicked. They said, no, we want to study the sun. This is not a bus which is going somewhere. That it can just be sent anywhere you want. So they renamed it to Aditya L1. So why is heating more efficient in the corona? So the main reason is that the corona is much less dense than the chromosphere. So given an amount of energy, it can raise the temperature quite quickly, because the mass whose temperature it has to raise is very low. And magnetic field plays an important role in the plasma dynamics of the corona. And that can also make it more efficient to heat the corona and keep it heated. So, yeah. Magnetic field. Okay, so that is, so there is a solar dynamo model, which basically talks of currents that are flowing within the sun in its interior, which is generating this magnetic field. So the magnetic field of this, so magnetic field is surprisingly quite rare in the solar system. There are only a handful of planets, and of course the sun, which have a reasonably strong magnetic field. The Earth is quite interesting, because although it's not a very massive planet, it does have a fairly strong magnetic field. So, but these are these sort of dynamo-based models that are there. Okay, so the inner planets. So these are all terrestrial planets, rocky planets. 4 planets are there, and they are characterized by their solid rocky surfaces, relatively small sizes, few or no moons, okay, and no ring systems. So these are the 4 planets, okay. And I think that's, I don't know what that last thing is. It's not the Earth's moon, it's too small for that. To check. So there is Mercury, Venus, Earth, and Mars. These are the 4 inner planets. They're all spherical and they are all rocky. Mercury is the smallest planet. It's closest to the sun. It has no atmosphere, and therefore extreme temperature variations are there. So on the dark side, it is very, very cold. And on the hot side, it is very, very hot. Has a heavily cratered surface, okay? And it has an unexpected magnetic field. So this was discovered recently. Initially, it was thought Mercury has no magnetic field at all, but it does seem to have some. Because you need to have a sufficiently large iron core for the dynamo models to work. And it was not expected that this will have a very large core because it's very small. Okay. So here's what it looks like. If you look at it at first glance, it looks like the moon, right? And in many ways, it is like the moon, except for that magnetic field business. In size, approximately, it's the moon. It has got a heavily cratered surface. It is almost tidally locked with the sun, which means its period of rotation and revolution are almost the same. But not exactly. Venus, similar in size to Earth, it has a thick atmosphere of CO2, extreme greenhouse effect, runaway greenhouse effect, as it's called, operates for Venus. It has got a very high surface temperature. I'm going to show you the surface temperature profile on, the temperature profile of Venus in the next slide. It has got what is called retrograde rotation, which means 243 days to turn on its axis and 224 days, 0.7 days to orbit the sun. So this is really weird. So what this basically means that its day is slightly longer than its year. This may be it's the only planet that shows this kind of thing. And there are various theories about why this may be happening. It may be some kind of collision early on, cause some kind of disruption in its rotation and so on. But not quite clear why this happens. But the interesting thing is, crazy thing about it is its temperature profile. It is quite transparent up to the upper atmosphere. Then there is a thin haze. Okay, and this is the main cloud layer. And that main cloud layer consists of concentrated sulfuric acid. Okay, so one cannot imagine a more inhospitable place in the universe. Then there is another lower thin haze. This is the altitude in kilometers. So about 50, 60, 70 kilometers above the surface is where these sulfuric acid clouds are. And then there is a thin haze. And again, it seems to be quite clear below. Okay. And these are, I think, the wind speeds which have been measured. This is the surface temperature on Earth, about 300 Kelvin. Melting point of lead is here. Here the temperature continuously increases. And by the time you hit the surface, the temperature is hotter than the melting point of lead. And I find it remarkable that 50 years ago, the Russians managed to land a spacecraft on its surface. Get a picture, one picture before it all dissolved in the rain of sulfuric acid or whatever it was. Yeah. See, CO2, even on the Earth, if we didn't have the oxygen, we would have high amounts of CO2. And we have high amounts of CO2 on Mars. We have high amounts of CO2 on Venus. On Earth, because of photosynthesis, we have CO2 in very low amounts. But actually, CO2 is a very common thing because carbon is common in the inner planets and oxygen is very common in the inner planets. And oxygen is a very reactive chemical. It's a very reactive gas. So it quickly forms compounds. On Earth, fortunately, it forms water, which is good. But it also forms, it would have formed carbon dioxide, but that carbon dioxide is completely sucked out from the atmosphere by the plants. That's why you have. And H2SO4 is not very large in quantity. So if you just measure the total amount of H2SO4 on Venus as a fraction of its mass, it's very small. But it's just that it's located in that cloud layer. So you have to pass through it to get to the surface. So which makes it very dangerous for spacecraft. Okay. So there's a concept in astronomy called albedo. Okay. It is the fraction of light that is reflected by a planet or a moon. It is 76% for Venus because it has a permanent layer covering of cloud. We can never see the surface of Venus directly. 100% of the time, there are clouds, these sulfuric acid clouds. And it's 30% for Earth. Earth also is fairly high because we have the sea and we have clouds also. Most of the time, they're reflecting the light and so on. But for the moon, which has no clouds, the reflectivity is only 7%. Earth, third planet from the sun, only known planet with life, 71% of the surface covered by water. And it has very uniquely, that's why I put it in bold, a nitrogen-oxygen atmosphere. Nitrogen is an almost inert gas. Oxygen is a very reactive gas. Under normal circumstances, it would not exist in elemental form. But it exists in large quantities in elemental form because of the presence of life. So you can think of this as a biosignature. So if you see another planet somewhere else, which has a lot of oxygen, that itself tells you that it may be very likely supporting life. It has an active geology and weather systems. Okay? This geology part is quite important. We'll come to that in a minute. So here's some people call this as a blue marble in space. And I think this picture illustrates it best. Also, India is bang at the center there. So I show this picture. The Earth's moon is very special because it is the largest moon relative to the planet size in the solar system. And it has synchronous rotation with Earth. What that means, its period of rotation is locked to its period of revolution. And because of that, we only see one side of the moon. The far side of the moon, we never see. It influences Earth's tides and stabilizes its axial tilt. It's so massive and relatively close to the Earth that it has a gravity impact on the Earth. Formation likely due to giant impact early in the Earth's history. So now Mars, it's the fourth planet from the sun. It's known as the red planet. It has a very thin atmosphere. So unlike Venus, which has a thick CO2 atmosphere, Mars has a thin CO2 atmosphere. Any reason why that may be the case? Small size, yes. So the surface gravity of Mars is significantly lower than the gravity of Venus. Venus's gravity is around that of the Earth, but Mars is, I think, 1/3 or so. And because of that, it can't retain all the gas that it has. It sort of escapes into space. So it has a thin atmosphere, mostly CO2. There is evidence of past water activity. Okay. Is this surprising? Presence of water anywhere, is it surprising in the universe? Huh? Liquid water is definitely, but water in some other form? Yeah. So it can exist because why? Because hydrogen is the most abundant element in the universe. It's quite reactive. Oxygen is also fairly abundant. So therefore, oxygen, carbon monoxide, carbon dioxide, these kinds of compounds are fairly common in the universe. So not totally shocking. And how did we get the evidence of past water activity? In some cases on Mars, you can see those channels like little streams and rivers that are flowing. That is evidence of past water activity. Though Mars may have been a bit warmer earlier. Okay. Whether it had life or not is unclear. Another thing, there are rocks which have slightly different chemical composition depending on whether they're exposed to water or not. And the Martian rocks, which we have analyzed, seem to indicate that they have come into contact with water at some point. So that is the evidence for passing. It has two small irregular moons, Phobos and Deimos. Okay, these are very small moons. Very likely these are some kind of captured asteroids. Okay, they're not real true moons, spherical moons like ours. On the surface of Mars, so this is a very nice image of Mars. And on the surface of Mars, there is a very large canyon, which is called Valles Marineris. And it is very long, okay, and also very deep. So it is something that is like the Grand Canyon, but on a much grander scale. And there's a big volcano there called Olympus Mons on the surface of Mars, which is the highest volcano in the solar system. It's also very huge in size. But of course, it's now inactive. It doesn't seem to have any activity at the moment. Mars, of course, all of you have read in the newspaper about how it is being explored by various spacecraft, including our own Mangalyaan. Beyond Mars is the asteroid belt. It contains millions of asteroids. And they could be really small. I mean, almost dust-sized particles to the dwarf planet Ceres, which is 940 kilometers in diameter, which is quite large. These are likely remnants from the solar system's formation. And these are also the source of most of the meteorites that fall onto the Earth. So this is the asteroid belt. Okay. And there are families of asteroids. So there are the Greeks, there are the Trojans, and so on. And they are in resonant orbits with Jupiter. Okay, so if they are located, for example, at the L3, L4 points of Jupiter, then they can stay relatively stable without their orbits being disrupted by Jupiter. And so you can see that they are trailing and leading the orbit of Jupiter. And right now, I think there are about of the order of maybe 30,000, 40,000 asteroids that are known. Many more will be discovered in the next decade, and I'll tell you why at some point. Okay. So outer planets, gas giants, Jovian planets, Jupiter, Saturn, Uranus, Neptune. They're characterized by their large size and mass. And they're primarily composed of hydrogen and helium. They have numerous moons and ring systems, and they have no solid surface except possibly rocky or icy cores. The core may be, because it's very highly dense, it may be liquid core or solid core. But on the surface, it's all just gas in the way down. So these again are true to size. So you can see that Jupiter is so much larger than the Earth, and Saturn is almost as large as Jupiter, but Uranus, Neptune are significantly smaller than these two. These two are quite similar to each other in almost every respect. But compared to the inner planets, these four are quite gigantic. And for scale, of course, here is the Sun, which is much bigger than all of them. It's the largest, Jupiter, largest planet in the solar system. Its mass is 2.5 times the mass of all the other planets combined. Okay, so the majority of mass in the planets is in Jupiter. It's got something known as the Great Red Spot, which is a storm that has been raging for centuries. We know that because since the time of Galileo, this kind of Great Red Spot has been recorded, and that storm has been going on. You can still see the Great Red Spot. It appears to be fading in recent decades. So maybe in 100 years or so, or 200 years, it will disappear. But it's been going on for a long time. It's got a powerful magnetic field. Okay? Of all the planets, it has the most powerful magnetic field. And it has at least 79 known moons, many moons. But 4 of those moons are special because they're very large, okay, comparable in size to the moon of the Earth. One of them, this one, Io, has active volcanoes. So when a spacecraft was sent to orbit Jupiter, they actually caught a volcano going off. Very rich in sulfur. That gives it a sort of yellowish color. And of course, it's very cold. And so when things come out, it's also the volcanoes behave differently than they do on Earth. First of all, there isn't much of an atmosphere, but also things are very cold. So any gases that get emitted often condense rapidly onto the surface. That's Io. Europa is again special. This is one of the places where water may exist. And very soon a mission, dedicated mission is going to be launched, whose main job is to figure out whether there is water on Europa. The water is likely to be subsurface because it's so cold that the surface itself is frozen over. But below the surface, below that frozen ice layer, there may be a ocean, water ocean. So they're trying to figure out if there is water on Europa. And Ganymede and Callisto are the 2 other moons, which are somewhat less interesting. And this is a picture of the Great Red Spot. Okay. So this brings me to just introduce a concept called brown dwarfs. Okay. So Jupiter is the largest planet in our solar system. It's about 300 times more massive than the Earth. But if it were significantly more massive, say Jupiter was 75 times more massive than what it is now, it would turn into what is known as a brown dwarf. And a brown dwarf is in some ways like a failed star. Okay? It can fuse deuterium and at the most massive, in the most massive brown dwarfs, it can fuse lithium as well. But it doesn't have enough temperature to do the regular thing of fusing hydrogen to helium. And therefore, Jupiter, of course, cannot initiate any nuclear fusion within itself. But brown dwarfs can fuse deuterium. They can produce small amounts of energy. It gets a bit complicated on how long they can survive and so on. But they do become bright enough to emit in the infrared. And with infrared telescopes, we are now able to detect brown dwarfs in the nearby regions of our galaxy. And I think about, if I remember correctly, about 6,000 brown dwarfs are now known. Okay. So now a question which is unrelated. We know that Jupiter doesn't fuse anything. But if you just observe Jupiter and find out how much energy it's radiating, it seems to be putting out more energy than it receives from the sun. Okay, how is this possible? Very good. That's right. Okay. So there is something known as the Kelvin Helmholtz contraction. Yes. Jupiter is shrinking by about 2 centimeters per year in size. And its internal structure is believed to consist of an outer mantle of fluid metallic hydrogen and a denser inner core. And then there is helium rain that falls from the top of the metallic hydrogen layer towards the center of the planet. Okay. And so it's the whole thing is contracting and generating kinetic energy. That kinetic energy is getting converted into heat eventually. And that heat is eventually escaping from the surface. So Jupiter is actually putting out more energy than it is receiving. Initially, incidentally, when people try to figure out why is the sun shining, of course, they had no idea about hydrogen fusion and so on. This is like 120 years ago. The model that they came up with was that the sun is slowly contracting and gravitational potential energy is being converted into heat. Okay, and then people said that, okay, let's work out the maths and find out how long the sun will shine. And they found out that it will shine for about 10,000 years. And for the Christian scientists, this wasn't much of a problem because they said the Earth was formed the whole universe was formed in some 4,700 BC. So obviously there is no problem. The whole thing can be 10,000 years old. However, around that same time, radioactive dating came into the picture and people started finding fossils which were 100 million years old, 200 million years old, and so on. And it became quite clear that this mechanism is not the right mechanism to explain the powering of the sun. So it was very soon, of course, quantum mechanics came into the picture. And then people were able to figure out what's actually powering it. But this mechanism is actually operating on Jupiter. Saturn is the second largest planet. Okay. It's known for its extensive ring system. It has the lowest density of any planet. It's less than water. So if you can make a seed, you could make a seed that could hold Saturn, Saturn will float on water. It has at least 82 known moons, including the largest moon, which is called Titan. Titan is so large and so bright that even with a relatively small telescope, you can see it. And of course, those 4 Galilean satellites. So Jupiter has a magnetic field. Saturn also has a magnetic field. And due to that, the solar wind produces aurorae. Okay. So at the pole of Saturn, you can actually see, so that blue color indicates ultraviolet emission due to charged particles sort of colliding with the atmosphere of Saturn near its poles. So just like you have aurorae phenomena on Earth, you can have aurorae on Saturn, you can have aurorae in Jupiter as well. Next planet, Uranus, third largest planet, ice giant. Instead of gas giant, they used to call all of these guys gas giants. But now the new term seems to be ice giant for Uranus and Neptune. There's water, there's ammonia, there is methane. Okay. And you will see that, I mean, if you just list which are the chemical elements that are present in abundance here, you will see that carbon, oxygen, nitrogen, hydrogen, the very relatively light elements occur very, very frequently. So these are fairly abundant elements. And therefore, these compounds are also very common. It has got a tilted axis of rotation. So the Earth is inclined to the ecliptic by 23 degrees. This thing is inclined by 97 degrees. So it's sort of completely on its side. And because of that, it's got a seasonal change pattern, which is quite crazy. It's crazy in the sense that for about half its orbit, one side is facing the sun. And then the other side comes. So it's like there's sunlight for many, many dozens of years and then complete darkness for dozens of years. It's got a faint ring system. In fact, all the 4 gas giants have rings. There are 27 known moons, and these are all named after Shakespearean characters. So this is a photograph. Uranus, its ring, and they're all named after different numbers. And these are all these Shakespearean characters. These are moons in orbit around Uranus. Neptune, outermost planet, it's another ice giant. Chemical composition is quite similar to Uranus. It was the first planet discovered through mathematical predictions. Okay. And so what people did was they measured the orbit of Uranus, and Uranus seemed to be getting perturbed by something else, which they're not accounted for, like Jupiter, Saturn, etc. So a calculation was made that, okay, there should be another planet, and approximately in this a part of the sky it should be present. And it was discovered soon afterwards. So I think 1846 was the year of discovery of Neptune. It's got, like the great red spot, it has a great dark spot. It's a large storm system. It has strongest winds in the solar system. Very, very high speed winds. It also has many moons, 14 moons, and the largest being Triton. Okay. So this is again a Hubble Space Telescope Wide Field Camera 3 image of Neptune. You can see the great red spot. There is here something called as a transient dark spot. There's a great dark spot which is quite persistent, but there are also some other dark spots which don't last for very long times. Okay, so dwarf planets, new category created in 2006. So in our when I was in school, we had 9 planets. Okay, now they've reduced that to 8. And it shouldn't have been made a planet in the first place. They should have called it. But then this thing got very politicized, actually. And there was a vote on whether Pluto is a planet or not at the International Astronomical Union meeting. And most people said, no, it's not a planet. So it got demoted to a new category called dwarf planet. So dwarf planet must orbit the sun and have sufficient mass for gravity to make them nearly spherical. But they have not cleared their orbital neighborhood. Okay, what does that mean? Is that if the Earth is so big and massive that if there is anything in the orbit of the Earth, it gets cleared up, meaning it sort of merges with the Earth. This it's not able to do because it doesn't have sufficient mass. 5 of them are recognized now. One of them was originally said to be an asteroid because it is entirely in that orbit. It is between Mars and Jupiter. But these are all far outside, beyond the orbit of Neptune. Okay. In fact, Pluto's orbit comes closer to Neptune. Another thing that makes these guys different is that all the other 8 planets, regular planets, they are almost in the same plane. That plane is referred to as the ecliptic. Okay? But I mean, they're not perfectly in the same plane, but a few degrees up and down. But these guys are in completely different planes. So Pluto is like sort of all planets are going like this. Pluto is going like this. So that's it. These are the dwarf planets. So the most famous dwarf planet, of course, is Pluto. It has a highly eccentric and inclined orbit. Okay. What does eccentric mean? Sorry? Highly elliptical. Yes, that's correct. It's not circular, but highly elliptical. The major axis is much bigger than the minor axis. It's smaller than Earth's moon, has 5 known moons, largest being Charon. And it was actually visited by a spacecraft, New Horizons spacecraft in 2015. And here is a photograph. That's Pluto, and that is its moon Charon. And the moon is so large that it can almost be considered as a dual planetary system. It's like a dual dwarf planet. The moon is also spherical. This is also spherical. And they are in orbit. So, okay, I think we'll stop here. There's a bit more in the solar system, which we will cover next time. And then we'll move on to extrasolar planets. So are there any questions? Sorry, one. They see one thing that's misleading over here. These are not so close to each other. Okay, they're very far. This may be a single picture, but that is taken in projection. That it's taken from an angle that they look close to each other, but they are quite far away from each other. So they obviously revolve around their center mass. Center of mass of, for example, the center of mass of the sun and Earth is inside the sun. So I don't know where the center of mass of this thing is, but don't be misled by the distance. Their relative sizes are correct, but of course they will be separated by much larger distance. Yeah. Dwarf planets are supposed to have moons. This is the only one that we know so far that has moons. Now, these dwarf planets are very faint, so they're not easy to find. So we don't know yet how many there are. We have found 5, but there could be 50 or 500. We don't know. And they're occupying a very large region of space. And since there's no predictive capability here. We don't know that, okay, in this direction, there should be a dwarf planet. We are just looking blindly and trying to find them. Incidentally, I forgot to mention that Surud More at Ayuka, he has a long-running project to what he calls Planet X detection or Planet 9 detection, he calls it now. So Planet 9 detection, so he's been using the Subaru telescope in order to image large areas of sky. And he's I think he's chosen some specific regions of the sky. And he's trying to find if he can detect a planet. But that he's not trying to detect a dwarf planet. He wants a full-size planet like Neptune. Not as large as Neptune, presumably, but something interesting. Yeah. There are models which predict that because gas is sort of lighter, it gets thrown out in a rotating system. It gets thrown out to larger distances. That is one model, but I'm not sure. We don't yet have enough statistics on what other systems look like. So this is a model that will explain our own solar system. But what about in other solar systems, if you find that rocky planets are very rare, or there are lots of gaseous planets nearby, or they're in reverse order? We don't know yet. The problem with extrasolar planets, as we shall see in the next lecture, is that there are lots of selection biases. Okay? Which means, for example, if you use the Doppler technique which measures the wobble in the position of the star. Then if the planet is very massive and very close, then the amplitude of the wobble is large enough for you to measure it. So if there are such planets, you will measure them. That doesn't mean they are very common. So it may be possible that there are much more common are distant low mass planets, but you can't detect them. So our selection is very biased, but we are getting there. And with the next generation of telescopes, which are specialized on finding Earth-sized planets, we will actually have fairly accurate statistics on how other solar systems are constructed.